All right, hope you guys are doing well this afternoon. Today we are going to be talking about Thevenin and Norton equivalent circuits. And this is going to be the first of two lectures on this topic. The next one will be Tuesday. Today we are going to focus on circuits that do not contain dependent sources, kind of learn the basics of Thevenin and Norton equivalent circuits. And then next Tuesday's lecture, we are going to talk about what happens when there are dependent sources included. All right. So the first thing that we're going to talk about is Thevenin's theorem. And I'm going to paraphrase it here. So in a nutshell, Thevenin's theorem states that you can replace any linear two-terminal network with an electrically equivalent voltage source VTH or V Thevenin in series with a resistance RTH or R Thevenin. So effectively, Thevenin's theorem states we can replace any two-terminal network with a practical voltage source. And we kind of saw a little bit of that in our class meeting on Tuesday, but there were very specific rules about how we had to do the source transformations that we were doing on Tuesday in order to get things down or simplify things to a smaller circuit containing just a voltage source in series with a resistance. Thevenin's theorem allows us to find that resistance and find that voltage in a different way as long as they are two-terminal networks. Okay? So the first thing that we're going to talk about is how to find the Thevenin voltage. Okay? So the Thevenin voltage VTH is the open circuit voltage seen at the terminals of interest. And I'm going to talk a little bit more about this terminals of interest bit here when we work an example. The Thevenin resistance actually, let me modify my Thevenin voltage expression really, or definition here really quickly. Thevenin voltage VTH is the open circuit voltage seen at the terminals of interest in a live network. That part is very important. So what a live network means is that all of the voltage sources and current sources in the system are left on. Okay. Now the Thevenin resistance RTH is the equivalent resistance seen looking into the terminals of interest in a dead network, where a dead network simply means that we are turning off all of our independent voltage and current sources. Okay, so to see how we can put this into use, let's work an example. So I'm just going to make up a circuit here. Volt source here. A 4 ohm resistor here. Let's put a 6 ohm resistor here. A 10 ohm resistor here. An 8 ohm resistor here. Let's put a 3 volt source down here. Two ohm resistor here. And then I'm going to put a load resistor here, RL. And that load resistor is what we're going to find the Thevenin equivalent circuit with respect to, okay? So this is our circuit of interest, and we are trying to find the Thevenin equivalent circuit with respect to the load resistance RL. So I'm going to write that down here. All right, and I'm going to do something really quickly to make my life a little easier here in a moment. I'm going to make a copy of this. Because we're going to be looking at it from a couple of different perspectives as we do this. I'm just going to press Control C and then go back to my bedroom. So the first thing that we're going to do is we are going to find our Thevenin voltage VTH. So according to Thevenin's theorem, our goal here is to determine the open circuit voltage seen at our terminals of interest. Since we're finding the Thevenin equivalent resistance with respect to this load resistor, what we're going to do is actually going to disconnect this load resistor from our circuit entirely. And this is going to give us the open circuit terminals that we're finding the voltage across. I am going to choose to put my positive polarity terminal on top and negative polarity terminal on bottom. And so this will be VTH. You might also see this as VOC, literally meaning the open circuit voltage. They both represent the exact same thing. So now our goal is to simply solve for this voltage VTH in any way that makes sense to us, okay? So if I'm looking at this particular circuit, the only simplification that jumps out at me would be to combine that 10 ohm resistor in series with that 8 ohm resistor into a single 18 ohm resistor. So I'm going to do that just really quickly. I don't see any other obvious simplifications that I can make. So now I'm going to go through and think about what kind of analysis that I could do here, right? So based on the complexity of this circuit, it looks to me like simple relationships like Kirchhoff's current law, Kirchhoff's voltage law, Ohm's law aren't really going to work out for us here. I don't see anything that I can do voltage division on. I don't see anything that I can do current division on. So now I'm going to look at nodal and mesh. Well, if I did nodal analysis, I would have one node up here that I don't know, another node here that I don't know, another node here that I don't know, assuming that my bottommost node is ground. So that would be one way to do it. Or I could do mesh analysis where I only have the two meshes that I need to deal with, the left-hand mesh and the top right mesh. This bottom right bit here will not have a mesh current because it contains an open circuit. So do you guys have any particular preference as to whether we do nodal analysis or mesh analysis for this?
I think mesh would be a little bit easier.
Okay, so let's take a crack at this with mesh then. So I'm going to define this to be mesh 1. And this guy up here to be mesh 2. Since I don't have any dependent sources, I don't need to write any controlling variable expressions since I don't have any current. So I can really just get straight to writing my KVL equations, right? So my KVL equation around mesh 1 I'm going to have negative 8 volts plus 4 ohms times I1 plus 6 ohms times I1 minus I2 plus 3 volts is equal to 0. When I do KVL around mesh 2, I'm going to have 6 ohms times I2 minus I1 plus 18 ohms times I2 plus 2 ohms times I2 is equal to 0. And so now I'm going to solve this system for I1 and I2. So I'm using a TI calculator today. This is a 2-equation, 2 unknown system. My coefficient for I1 looks like 4 plus 6 is 10. My coefficient for I2 in my first equation is negative 6. And then I'm going to have 8 minus 3 is 5. In my second equation, looks like I have negative 6 I1. 6 plus 18 plus 2 looks like 26 to me. Constant term of 0. And so solving for these currents, I get 65 over 112 and 15 over 112, respectively. So now that I know these mesh currents, I need to figure out how to determine the voltage VTH. So what I'm going to do, now that my mesh currents are known, is I'm going to write a KVL equation around this path, right? So I'm going to write here KVL at bottom right. So that's going to look like -3 volts plus 2 ohms plus VTH is equal to 0. So just to be very, very clear here, I chose to express the voltage drop across the 2 ohm resistor with this particular polarity, which is where this plus sign comes from. And then because the current I2 is flowing into the negative polarity terminal, that's why that negative sign shows up there. Rearranging this, I would have VTH is going to be equal to 3 volts plus 2 ohms times I2, where I2 is 15 over 112 amps. And I'm just going to throw that into my calculator really quickly. So 3 plus 2 times what I have stored in my calculator is Y. I wind up getting 183 over 56 volts, or in decibel form, 3.268 volts. So that's what I got for the Thevenin voltage, okay? So let me just recap things really quickly here. When we are finding the Thevenin voltage with respect to a particular circuit element, the load resistor RL in this case, we take that circuit element out of the network. In doing so, it leaves behind an open circuit set of terminals, and those are the terminals across which we are trying to find our open circuit voltage. In your homework problems, you will have some problems like this, where you're trying to find the Thevenin equivalent circuit with respect to a particular element. You will also have problems where you're trying to find the Thevenin equivalent circuit with respect to a particular set of terminals. When you're finding it with respect to a set of terminals, there's no need to remove an element because you already have an open circuit to work with, okay? So the process is the same, but only when you're finding it with respect to a particular element do you need to actually remove the element from the network. You can find this Thevenin voltage or open circuit voltage using literally any circuit analysis technique that you are comfortable with. It does not particularly matter. We chose to use mesh here because it's a 2-equation unknown system. Nodal analysis would have allowed us to calculate for the voltage at this node directly, and choosing ground as our bottom node means that whatever node this was, let's just call it VC for the sake of argument, would have been the same thing as VTH. So effectively, nodal analysis and mesh analysis wound up being the same number of steps because of the topology of this circuit. All right, so our next step is going to be, well, actually, before we do that, anybody have any questions about what we did here to find the Thevenin voltage? All right, so our next step is going to be to find our Thevenin resistance. So let me put that circuit here where we can see it. Scooch this down a little bit. All right, so we're finding the Thevenin equivalent resistance with respect to that load resistor RL as well. So once again, we are going to remove this load resistor. These are our open circuit terminals that we're going to be looking into. But to calculate Thevenin resistance, we need to be looking at a dead network, okay? So what does a dead network mean? Well, it means that our voltage sources are turned off. And hopefully you recall from our lecture on superposition that to turn off a voltage source, we replace it with a short circuit. So now we're just going to use resistance combination techniques, if at all possible, to figure out what the equivalent resistance for this circuit is. Okay. So this isn't something that I can just look at and figure out. So I'm going to label my nodes. Right. So here's one node. Here's a node. Here's a node. And let's do purple. Here's a node. I'm going to label these nodes. So I'm going to call this A, this guy B, this guy C, and this guy D. So putting A on the left-hand side of my screen and putting B on the right side of my screen. From A to B, I can go through the 2 ohm resistor. I could also go from A to C. So let's put C here. So to go from A to C is the 8 ohm resistor. I can go from C to D through the 10 ohm resistor. So let's put D here. And then I can go from D to B through either the 4 ohm resistor or the 6 ohm resistor. So I'll put the 4 ohm resistor up here. And the 6 ohm resistor here. So I'm just going to double check these things really quickly. So directly between nodes A and B, I have the 2 ohms, which is this guy right here. So that makes sense. Between A and C, I have the 8 ohm resistor. So that one checks out. Between C and D, I have the 10 ohm resistor. So this guy checks out. And then between D and B, I have 4 here or 6 here. So I believe this is the network that we can use to find this equivalent resistance. So let me just do some simplification here. 4 in parallel with 6 is going to look like 4 times 6 over 4 plus 6. So that's going to be 24 over 10. So let's just call this a 2.4 ohm resistor. Now I have all of these in series. So 8 plus 10 plus 2.4 looks like 20.4 to me. And so our Thevenin equivalent resistance here is going to be 2 times 20.4 over 2 plus 20.4, 40.8 over 22.4. And I'm just going to leave it like that, although this could be simplified further. Okay. So there's our Thevenin equivalent resistance. So let me recap what we did here. Okay. We started with our original circuit. Since we're finding the Thevenin equivalent resistance with respect to a particular circuit element, we took that circuit element out, leaving behind an open circuit set of terminals. These are the terminals that we're looking into to determine our Thevenin equivalent resistance. The Thevenin equivalent resistance is always determined, at least if we're trying to calculate it directly like we are here, by looking at a dead network, where a dead network simply means that all of our independent voltage and current sources are turned off. Since this circuit contained two independent voltage sources, we turned both of those voltage sources off by replacing the voltage sources with a short circuit. And then we were able to use simple resistor combination techniques in order to figure out what the resistance between that open circuit set of terminals was. So what this means, if we put all this together, is that our original circuit and the circuit that I'm about to draw are electrically equivalent. So this will be that 40.8 over 22.4 ohm resistor. Because I don't remember what the Thevenin voltage was off the top of my head, 183 over 56. These two circuits are electrically equivalent according to Thevenin's theorem. Okay. So we get the exact same results as we would have gotten by doing source transformations and all that kind of stuff, if there were any available, in a different way here, right? And this method, using the Thevenin equivalent, so finding VTH and finding RTH, will literally work for any linear circuit where we can look at it from the perspective of being a two-terminal network. All right, so before we talk about Norton equivalent circuits, any questions on this Thevenin equivalent representation? What would change if the 6 ohm resistor was in the spot below it is currently? So by that, you mean if the 6 ohm resistor no. So if the 6 ohm resistor were in the place of the 3 volt source, would this 6 ohm resistor still exist? Or would it be a short circuit or a different resistance or an open circuit? It should. So let me scroll up here really quickly, right? So the question in the chat, so to speak, is what would happen if there were a resistor right here? Well, effectively, that means that we would have a different node here. Let's call it E for the sake of argument. And so our connect the dots of finding the equivalent resistance would look vastly different because now we have one more node. Yeah. So if we had a resistor here call it RX, regardless of what its value is, it would likely change the equivalent resistance of the network pretty significantly, which actually brings me to a slightly related topic to On Point. So we found the Thevenin equivalent resistance with respect to the resistor between this set of terminals. If we found the Thevenin equivalent resistance as seen by this 8 ohm resistor, we would actually get a different result, right? So what element we're finding the Thevenin equivalent circuit with respect to will absolutely change our results. So that's why it's important that we really reanalyze the circuit for every step, because that's something that I've seen students make mistakes on. They find the Thevenin equivalent voltage and then do some weird thing to find a Thevenin equivalent resistance and then don't understand why they got the answer incorrect. And it correct parameters. So to find the Thevenin equivalent voltage with respect to a particular element, once again, you will take that element out of the circuit, leaving behind an open circuit set of terminals, and then use whatever circuit analysis method makes sense to you to determine that open circuit voltage. To find the Thevenin equivalent resistance with respect to a particular element, once again, you take that element out, leaving behind an open circuit set of terminals. You turn off all of your independent voltage sources and current sources, and then you find the equivalent resistance seen between those two terminals. 2 separate steps, 2 separate circuits to analyze. Any other questions? All right, so let's talk about Norton's theorem. So Norton's theorem is effectively the exact same thing as Thevenin's theorem, except that we're going to wind up with a practical current source representation of our circuit instead of a practical voltage source. Norton's theorem states that any linear 2-terminal network can be replaced by an electrically equivalent current source which we're going to call I Norton, in parallel with a resistor, which we're going to call R Norton. So the Norton current I Norton is determined by shorting the terminals of interest and calculating the current flowing through that short circuit. The Norton resistance R Norton is the equivalent resistance seen looking into the terminals of interest in a dead network. So the Norton resistance is literally the exact same thing as the Thevenin resistance. So I'm going to make a note of that here. R Norton is the same thing as R Thevenin. So from this point forward, you will literally never hear me talk about R Norton again. Everything is just going to be R Thevenin. So if we wanted to find the Norton equivalent circuit for the circuit that we were just analyzing a moment ago to find the Thevenin equivalent, let's talk about what we would do to find our Norton current. So here's our circuit. We're going to remove that resistor RL because we're finding the Norton current with respect to that load resistance. I am going to now short circuit those terminals. So effectively, when we're finding the Thevenin voltage, we replace our element of interest with an open circuit. When we're finding the Norton current, we replace our element of interest with a short circuit. And we're going to find the current flowing through our short. This is commonly referred to as I Norton. You may also see it as ISC for short circuit current. Okay. And we this current using literally any circuit analysis method that makes sense to us. So I am going to choose to do mesh analysis here, where this is mesh current I1, this is mesh current I2, and this is mesh current I3. Let's write our KVL equations. So at mesh 1, this is going to be the exact same mesh equation that we had earlier. -8 volts plus 4 ohms times I1 plus 6 ohms times I1 minus I2 plus 3 volts is equal to 0. For mesh 2, going to be very similar to what we had earlier. 6 ohms times I2 minus I1 plus, I'm going to put that 10 ohm and that 8 ohm resistor together because they're just in series. 18 ohms times I2 plus 2 ohms times I2 minus I3 is equal to 0. And now we're going to have KVL at mesh 3. So that's going to be -3 volts plus 2 ohms times I3 minus I2 is equal to 0. Solving this system for I1, I2, and I3. Give me a moment to throw this in the calculator. So now we have a 3x3 system. My coefficient for I1 is 4 plus 6 is 10. My coefficient for I2 is -6. My constant term is, my coefficient for I3 is 0. My constant term is 5. In my second equation, my coefficient for I1 is -6. My coefficient for I2 is 6 plus 18 plus 2, so 26. My coefficient for I3 is -2. My constant term is 0. In my third equation, my coefficient for I1 is 0. My coefficient for I2 is -2. My coefficient for I3 is +2. My constant term is +3. Solving this system, I get I1 to be 23 over 24 amps. I2 to be 5 over 17, and I3 to be 61 over 34 amps. And we can see by inspection here that I3 and I Norton represent the same current. So my Norton equivalent current is 61 over 34, which means that this circuit and this circuit, let's scroll up here because I don't remember what this resistance was off the top of my head, 40.8 over 22.4. These two circuits are electrically equivalent to each other, okay? So let me just title this really quickly. So if our Norton equivalent circuit is electrically equivalent to our original circuit, and our Thevenin equivalent circuit is electrically equivalent to our original circuit, then it stands to reason that these two circuits are electrically equivalent to each other as well, right? And we can prove that actually pretty quickly here, right? So effectively, the Norton equivalent circuit is the source transformation of the Thevenin equivalent circuit. So what we should see is that V Thevenin will be equal to I Norton times R Thevenin, or expressed in a slightly different way, I Norton should be the same as V Thevenin divided by R Thevenin, or in a third slightly different way, R Thevenin should be the ratio of V Thevenin to I Norton. So let's just test this really quickly here. Our Thevenin voltage, let me scroll up so we can find it, 183 over 56. Our Thevenin resistance, 40.8 over 22.4. Throw this in my calculator. Hope that my mental math when I was doing the resistance combinations come out to be correct. I get 1.794 and some change amps. 61 divided by 34 is 1.79411 some change. So when we're analyzing circuits to find their Thevenin and Norton equivalent circuit, we can actually think of this in two ways. If I can find two of the quantities, so either the Thevenin voltage, Norton current, or Thevenin resistance, if I can find two of those, I can automatically know the third one just by taking the ratio, or I can find all three of them, all three quantities, and use that as a means to check my work, because those relationships must be satisfied. Okay. So let's work one more example problem, and then I'll let you guys go a little bit early today. So let's say that we have the following circuit. And I want us to find V Thevenin, I Norton, and R Thevenin with respect to terminals A and B. I'm going to make a note here. We're going to do positive polarity on top, and the direction of our current will be down. I usually specify which terminal to put to consider to be the positive polarity term Norton current with when I write problems for the exams and all that kind of stuff. It's not always given to you in your homework problems, but effectively, if your positive polarity is on top, your current should be flowing down. If your positive polarity is on bottom, your current should be flowing up, etc. So let's find VTH first. So since I already have an open circuited set of terminals, I'm literally just looking for this voltage, which is going to be the same thing as the voltage drop across the 5 ohm resistor. Looking at this circuit, I'm going to either do nodal or mesh here. I'm going to choose to do nodal analysis so that we can solve for VTH directly. Okay. So I'm going to call this node A, this node B, this node C, and this bottom node ground, so that VC represents the exact same thing as my Thevenin voltage, because the positive polarity terminal of V Thevenin is at VC, and the negative polarity terminal of V Thevenin is at ground. So VTH is equal to VC minus 0 or VC. My voltage relationship, I'm going to have VA is equal to 12 volts. Now I'm going to do KCL at node B. So that's going to look like VB minus VA over 13 minus 2 amps plus VB minus VC over 10 is equal to 0. Now I'm going to do KCL at node C. So that's going to look like VC minus VB over 10 plus VC over 5 is equal to 0. Solving this equation for the system of equations for VA, VB, and VC. Let's see, so my first equation, I have 1 VA, 0 VB, 0 VC is equal to 12 volts. Yes, I am that lazy that I would put that into my system solver. In my second equation, my coefficient for VA is -1 over 13. My coefficient for VB is 1 over 13 plus 1 over 10. My coefficient for VC is -1 over 10. My constant term is 2. And my coefficient for VB is -1 over 10. My coefficient for VC is 1 over 10 plus 1 over 5. My constant term is 0. Solving this system, I get 12 volts, no surprise there. 285 over 14 volts here, and 95 over 14 volts here, where once again VC is the same thing as V Thevenin. Okay. To find my Norton current, I take my circuit. Now I am going to short circuit these terminals and find the current down. Okay. So I'm going to do something here. I'm going to explain what I'm going to do. Because my 5 ohm resistor is shorted out by the short circuit between terminals A and B, I'm going to avoid it when I write my mesh equations here. So I'm going to have this current as I1, but instead of doing I2 and I3 like this, I'm going to do mesh around here as just I2. The reason that I'm able to do this is because I know that no current is going to flow through the 5 ohm resistor. So all of the current that's flowing to the right from the 10 ohm resistor is going to flow through that short circuit. So I'm just eliminating an equation from my system by understanding how the circuit will behave, right? You would get the exact same result if you wrote a 3-mesh equation. I'm just trying to make this more simple. So because I have a current source, I can say that 2 amps is equal to I2 minus I1. And now I'm going to write a KVL equation around the outside. So that's going to look like negative 12 volts plus 13 ohms times I1 plus 10 ohms times I2 is equal to 0. I'm going to solve this system for I1 and I2. So my coefficient for I1 in my first equation is -1. My coefficient for I2 is +1. My constant term is 2. My coefficient for I1 is 13 in my second equation. Coefficient. Solving this system, I get I1 to be -8 over 23 amps and I2 to be +38 over 23 amps. And I2 is the exact same thing as I Norton. So if I've done this correctly, these first 2 steps, R Thevenin should be 95 over 14 volts divided by 38 over 23 amps. Throwing this into my calculator really quickly. 115 over 28 ohms. Let's check things by finding RTH directly. So I'm going to look into this set of terminals. With my current source turned off, which means it's open circuited, and my voltage source turns off, which means it's short circuited. So to me, this is going to be 5 ohms in parallel with 23 ohms. So 5 times 23 over 5 plus 23, 5 times 23 is 115. 5 plus 23 is 28, and we got the exact same result. Okay. So we must have done all of the steps correctly. If we didn't, one of these answers wouldn't match the others. Okay. All right, so I've worked an example of finding the Thevenin equivalent circuit with respect to a particular, or excuse me, Thevenin and Norton equivalent circuit with respect to a particular circuit element. I've also now worked an example problem of finding the Thevenin and Norton equivalent circuits, or at least the parameters of those circuits, with respect to a set of terminals. So does anybody have any questions regarding this material? Alrighty, well, I'm gonna let you guys go early today so that I can go and continue to help out with. You have any questions or anything regarding the upcoming exam on your choice of Monday, Tuesday, or Wednesday, please do not hesitate to email me or shoot me a text. I would be happy to answer your questions if you have any. Thank you very much and have a great rest of your afternoon.
If you don't mind real quick, is there anything you would recommend us looking over for the exam?
So for the exam, the practice tests that I uploaded are good things to practice from. The in-class assignments, I feel, are pretty good things to practice from as well. I'm not really keen on many of the homework problems that you've seen for this first section of the course. So, you know, working your homework is always good practice, but if I were trying to focus on things to study for, I would limit myself to the practice tests or the old exams and the in-class assignments. And like I said, if you run into anything that doesn't make sense or you just need clarification on, by all means, please let me know and I'd be happy to answer your question.
All right, thanks. Have a good day.
Sir, for
Yeah.
the exam, is it just it will open at a certain time on Monday, Wednesday, Friday, and we go on the Moodle and like set everything up and then do it, or do we have to like go ahead and confirm it with you when we're taking it?
You do not have to confirm it with me at all. So I will have a version of the test for Monday afternoon, Monday evening, Tuesday afternoon, Tuesday evening, Wednesday afternoon, Wednesday evening. And you just take whichever one of those works with your schedule and your level of preparedness. You don't need to confirm anything at all with me. That being said, whichever one that you attempt first is the one that your grade is going to come from, because I've definitely had students try to take it on a Monday and then come back and take it on a Wednesday and see if they did any better. Whichever one you take first is the one where your grade shows up from.
All right. Thank you, sir. You have a nice one.
You too.